Hi, and welcome to the second video in creating our DLX architecture simulator. So last time we were starting on our state machine and our very basic initialization sequence. Today we're going to hopefully flesh that out a little bit more and hopefully get some state transitions done, but we'll see where time takes us. So since last time, I haven't done much to the state machine. I mainly changed the comments from log this to do add logging, and then in the register file handler .h, I added a const uint r0, and that's because we can use struct declaration and instantiation where you kind of do it without declaring as a pointer. So gp registers gp equals, and then you use this here, and you would specify 1, 2, 3, where these would correspond to the registers. And then, so we could do, for example, 0, and then that would instantiate maybe all of them, but for sure R0 to 0. And then from there, you would use memcopy to copy GP into a pointer. So it gives us that option, and we have the option of leaving it const, where it will throw us compilation errors if we try to assign to R0, which may be something we want to avoid in the future. So we have the option of taking that out very easily, and it also lets us, because we want to have it whenever something is assigned to R0. So if you do add R1 and R2 together and you store it in R0, it'll always be 0 no matter what values are in R1 and R2. We want this to always be a 0 value, so we may have to leave this as not a const and handle it, or we could just ignore any operation that goes to there. We have tons of options that we'll take a look at when we get to that point. And then the only other thing I changed was in state machine, state handler.h. I added just a int dummy value. That's just to remove compilation errors until we actually put stuff inside of this struct. So other than that, nothing's changed. Everything else is the same as the previous video. So with that, we will get started today by drawing a little diagram of how our state machine is going to transition between states. And this is a good thing to know so that we know what states to implement and kind of how the flow of the state machine is going to be. So we'll start with that as my computer tries to catch up here. So let's open Photoshop. Oh, it was caught up. It's just the white screen threw me off. It's too much dark and white. Anyway, so our first state is going to be instruction. Actually, that's not right at the whole thing here. Oh, that's not what I want. Haven't used Photoshop in a little while. So we have instruction fetch. So that's going to go to itself. If there's no instruction to fetch, it'll just keep looping through it until it gets an instruction. And then when it receives an instruction, it will go to instruction decode. Instruction decode will then execute the instruction. So this is where the actual logic gets done. So if it's a jump, it will go to the location. If it's an add, it will add the two values together. If it's a load or restore, it will go and get the stuff from memory. The only time, so the one weird case here, and maybe we should actually make that closer to kind of handle this better, but a little bit of finickiness here. So on a no operation, we will go from execute to instruction fetch because there's no reason to go through the other two. We may go through the other two if we want to keep a consistent 5 cycle per operation or per instruction, but that's something that we can handle later. it's probably a good idea to go through the other two stages as well, and maybe just not do anything. Um, Actually, that probably is a better idea now that I think about it. It'll make handling things better. So that changes a lot of stuff. So essentially, we'll have instruction fetch, which will loop to itself, and then we'll go to instruction decode. We'll go to execution. We'll go to mem, or memory access, and then we'll go to write back, and then we'll go back to instruction fetch. So it's actually a lot simpler when you do it that way. A little bit of thought goes into the process. So yeah, no matter what, you'll always have 5 cycles, and that's to keep a consistent rate. If you wanted, there's actually nothing stopping you from adding all kinds of catches, like a no op goes here, a jump or a load or an add or anything not accessing memory skips that and goes there. It'll prevent you from doing a lot of optimization. For example, if you have something accessing register 1 in this instruction, and then in I3 it also needs to access register 1. This is called a data hazard, where this will not be done with register 1 by the time this one does need it. So there's ways to handle that, and if you don't have a constant number of steps in an instruction, it makes it hard to account for whether or not this will happen. But the nice thing about doing this in software and not at a hardware level, or a very, very low level, that's much lower than what we're doing, is you can actually have catches for this in your C code, and you can have all kinds of funny optimizations. So you could optimize this in any way you want and not stick to a rigid five stage cycle. It's just a matter of whether or not you want to do that. Maybe you want to see whether it's faster or not. There's no right or wrong way to do this. This is just the way that I'm going to start out doing it, to keep it consistent and constant. But again, there's no right or wrong way to do this. So if you want to do it that it's a 3 or a 2-step process, if you want to do it that it's a constant 5, you design it however you want. There's no right or wrong way of doing it. But that's the flow of the way I'm going to be doing it. So we'll always go either to fetch, which will consistently loop on itself until it gets an instruction. And this is going to be more relevant when we have no file to read from, because we'll have to loop and loop and loop until we have a instruction entered in via the command line, or however we decide to implement that. But then once we have that in place, and we have file reading in place, then this will just loop and loop and loop until, or this will loop through until it gets to the end of the file, and then it will just loop on itself until the machine is halted. So that's our state transition diagram. So that's how we're going to be navigating between these states. So inside of statehandler.h, where we'll handle our states, we will need to have our different states, and we'll need to have the incoming state and the outgoing state. So there's 2 ways of thinking of a state. We can either think of each state as an individual, for lack of better words, object, where it has its own, it's like the registers get passed in and it acts on them, and then it passes it to the next state. So the state it's essentially the state is stationary, but the data transitions between the states. The other way of thinking of it is the data is stationary inside of a state, but then the state goes through the different states. So to kind of put this into a picture, we'll go back to our Photoshop here, and we'll diagram it out. So we'll kind of just clear this. So we'll just grab it all really quick and then delete it. Okay. didn't work at all. Alright, so apparently deleting is a lot more complex than one would simply imagine. So what we'll do is we will erase all this manually, really quickly. So the two ways of thinking of it are, so first of all, we'll have an instruction fetch stage, an instruction decode stage, an execute stage, memory access stage, and a write back stage. And then we would have our instruction, which has the opcode and then the rest of the data. So the first way of thinking of it is to go and pass this into here, and then so this is the fetch. I guess the fetch it's more of a pull, I guess the way of thinking of it. But this instruction gets pulled from memory and passed to here, and then this will decode it and say, okay, we have this. So it says, okay, opcode equals this function, and then it would pass the function and the parameters to execute, who would then call the function. I should remove that. So let's write in here and then out the function and parameters, and that would go there. And then here we would actually call the function, and then we would have whatever it returns. We would have some kind of data, however we decide to implement that, which would then be passed on to memory, and then memory would act on it if it needs to, and then it would go to write back, and it would act on it as it needs to, and then it would be done. So in this way, data is being passed around between state objects, and they're acting on it in their own way. So that's the first way of thinking of it. The second way of thinking of it is the instruction still gets pulled to fetch, or to instruction fetch, and then instead of data going over to in the instruction decode, the entire state goes to decode. And in this way, everything stays internal to the state. So the data never leaves the state. So it would go to decode, where it would have the instruction inside of it. So instruction's still in here, and then it would become an opcode, or it would become a function with parameters. And then instead of it passing that on to execute, it transitions into execute. And execute then says, okay, we're going to call the function, and we're going to have whatever it does inside of us. And then we'll transition to memory, where we will have memory go into the memory if we need it to. And then it transitions into write back, where it writes to the registers if it needs to. And then it transitions, instead of transitioning into done, and I guess this doesn't really transition to done either, they would transition into new fetches. So this would be then a new data that IF fills with a pull. So that's another way of doing it. So those are the two main ways of doing it. So in option 1, you would have 5 data objects. So say an array of 5 datas. and in here you would have 5 states. Now, which one is better? I don't know. Which one is easier to implement? I don't know. Which one's more efficient? Which one's smarter? Which one's more practical? There's no right answer. Both of these ways will work. Both of them will do what they need to do. One may require 10 more catches or 10 more cases that it has to count for, but they both will work and they both will do what they need to do. If you want to implement one, feel free to implement one. If it's the one I'm doing, just follow along. If it's not, feel free to do your own thing. Software development's great that way. There's no right or wrong way to do things. There's nothing stopping you from saying, hey, I want to try doing it my way instead of your way. It's what an experimental science is all about, and we're in one of the most experimental sciences with computer science. So do whatever you want. I'm liking this state system a bit better. The last instruction set simulator I did, I used the data method. And it was kind of interesting. It kind of made a few things a little bit interesting, but it worked. It did what it needed to do. So this time I'm going to try this, and worst case it doesn't work, and we just say, okay, scrap this, go here. But we will start by trying out this system here, where we have a state a state object that transitions between states. So let us start implementing that system. So what we'll do at first is we'll need to figure out what we need in our state. So our state's going to need to know, we're going to need to know the current state we're in. We're going to, actually we should call this a stage now. So current stage, the state is in. We're going to need to know, so we're going to need the instruction. We're going to need to know the opcode and the parameters. So the parameters can either be 3 registers, 2 registers, and an immediate or hard-coded value. This would be like add 10 to R1 and store it in R2. That would be, the 10 would be the immediate value. It can also be a address or a register and a memory address. We got a couple different options there, but it's going to be the opcode and the parameters essentially. And then we'll need to know the function to execute based on the opcode. So we could either just go to and say, either go a function opcode and just call it that way, or we could go and say function equals table, our function table opcode execute, and then another one go function execute. So there's a couple different ways to do it depending on what we want to do. So we'll need the function, and then we'll need, I would say, a uint for storing the result for something where we're adding, subtracting, any kind of basic operation where we're going to be writing it to a register. Actually, we should a result actually. So this will be either register value in assumption that's like a 3 register instruction, or a 2 and an immediate value instruction, or loaded stored data, or loaded and to store data. So this is if we're calling a load or a store command. And then after that, that should be it. The other two will handle it as we need to. The other nice thing about having the states is that we can have access to them from other states. So, for example, oh, I closed it. If we need to access here, and I'm using my mouse. So, if we need to access this state to find out what registers it's using, or to access this state to find out what registers it's using, or this state for processing data hazards, that's something we can do in here. We can have a list of registers, and then put a question mark there. So that's just another way of handling data hazards if we want to. So let's create a enum, and we'll call it stages. So one thing you can do is you can always prefix stuff like these enums and structs with your project header like we did the header file here with the DLX. I don't think it's really necessary since we shouldn't have any conflicts, but it's always an option. So we'll have our stages here. We'll have instruction fetch. I don't really know how I want to call. I'll go instruction. We'll use camel case. Instruction fetch, instruction decode, instruction execute, memory access, and then write back. I guess it should be enough, doesn't it? Okay, so this is our 5 instructions. So we'll need stages, current stage, and then the instruction. Let's just quickly see how big the instruction is. I'm pretty sure it's 32 bits, so we can use our uint, which we don't have access to because we don't have it included. So let's make another header file, just like we did with errors, errors.h. We'll make a header file and we'll call it DLX. Actually, let's call it DLX.h. Right? Yeah, that should be. Call it DLX sim. Kind of closer to the project name, because the project name is DLX sim. So we'll call it DLX sim.h. And inside of this, we will have a if and def DLX sim h, define DLX sim h, and if. So this kind of, I guess we could prefix it with DLX underscore DLX sim if we wanted to stick to pattern, which doesn't make a difference. But anyways, in here we're going to have stuff that needs to be included in all of our files. So this header file will always be included with every single header file we ever include. Just so every single file has it that needs it, and it'll say stuff like typedef, unsigned, integer, uint. So now we have access to our uint from everywhere. So let's include that here. Include DLX sim. And then we can have a uint for our instruction. Just like that. So what we'll do is we'll delete this one and we'll include DLX sim. And we'll go to errors. Won't need it. Because that's also a constant kind of thing. So I'll put it in here as well. Include DLX sim. So there we go. So now all of our files header, actually put at the top. Just because that way if we can actually sum like this then, where we have remove header errors. So yes, nothing has it. Okay, and then we go up here and we go include errors. And now every file has access to errors as well. So if we need to add an error, everybody will have access to it because everybody has access to DLX sim. So it's just a nice way to have includes, specific includes everywhere. So we could add, you know, stdio, stdlib to that if we want. Actually, that's probably a good idea. Let's do that right now. Include stdlib, include stdio.h. So now every single file has access to printing and to lib, which is, we may want to pull that out later depending if nobody uses it, but right now everybody has access to it. If we need to print somewhere, we can always be able to print. So we can even wrap this in a if do not debug flag where we only want to do this if we're debugging, or all kinds of options. But for right now, that's good enough. So back to our state handler. So we have our stage, we have our instruction, and then we're going to need to have something for the opcode. So the opcode is going to be the instruction for the deluxe. So I'll put it in here. We'll have a nice little header. So okay, and then so an instruction format. So let's fill this in. Just make it nice and pretty. So instruction. The format of the instruction is I should just not do that. So the instruction format is, so let's do our type first. So we have 31 to 26. So let's put bits, and then tab this over. 31 to 26 will be 0x0, so always zeroed out. 25 to 21 will be register source 1. 20 to 16 will be register source 2. And 15 through 11 will be register destination. 10 through 6 will be unused. And then 5 through 0 will be the opcode. And then we have I type. And there we have bits. And then we have 31 through 26 will be, actually maybe this we can put on the same line so it doesn't get super long. There's nothing's worse than a very long file. It doesn't have to be long. Bits. Oh. So then I guess, yeah, the 31 to 26 is opcode. 25 to 21 is register source 1. 20 through 16 is register destination. 15 through 15 through 0. So the remaining 16 bits are the immediate value. And then we have JType. And there we have bits, and we have 31 through 26 is the opcode, and then 25 through 0 is the value. So JType tends to be jumps, or it's got a couple other types of jumps, more or less, but they will be where you're jumping to. So let's put some examples here. So example instructions. So let's say our type. So let's see if I can find an example here. Let's see. It's kind of hard to. So here's a list here of the instructions. I will make sure to include it in the video description. But it's all the instructions that an implementation of DLX must support, and kind of what they do. But we would have, so if we wanted our R-type to emulate the flow, we would have 1, 2, so let's write it in bits first. So it would be 1, 2, 3, 4, 5. Actually, let's go R-type. Let's go add RD equals RS1 plus RS2. So if that's the instruction you want to execute, we would have 0, 0, 0 for the add. So register source 1 would be, actually let's do an example here. Let's say if we want to add R5 equal to R1 plus R2. So we would have to do 0, 0, 0, 0 for the first 5 bits. R0 would be another 5. And then R1 would be an, no sorry, that would be 1, 2, 3, 4, 5. and then we would have R2, which would be 1, 2, 3, 4, 5. So this says 0, and this says 1, and then destination would be 5, so that would be 4 and 1, so 1, 2, 1, 0, 1, and then we would have 4 that were unused, or sorry, 5 that were unused, and then 6 for the opcode, which is 20. Actually, it's 0x20, which is hexadecimal. So 16 to the 1 times 2, so 32. Which is 32 in binary is, so we have 6. So 1, 2, 4, 8, 16, 32. So that should be just 1 like that. If my math is right, which it should be, but there's always uncertainty. So anyways, that would be a instruction, and it should be 32 bits. So we have 6, and 5 is 11. Man, my math is bad. And 5 is 16, and 5 is 21, and 5 is 26, and that's 31. So something's wrong. I'm pretty sure something's wrong here. Let me just double check my math. 31, 30, 29, 28, 27, 26. So this should be 6 at the beginning. So we have 31, 30, 29, 28, 27, 26, 25, 24, 23, 22, 21, 20, 19, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Perfect. So that should be the right number now. Then again, I'm having a bad math day, so everything could be wrong. Anyway, so let's do an I-type example now. So we'll do a very simple one of add I. And we'll say R5 equals R1 plus 10, where this is the immediate value. So this time, we would have, so add I. So this time, instead of it being 6 bytes for zeros, it's 6 bytes for the opcode. So the opcode for add I is 0x08, so that's just 8. So we would have 6, 1, 2, 4, 8. So 1. And then we'd have register source 1 of 5. So that is R1. So exactly the same. And then register destination is now this value. Boom. And then we have the immediate value as the remainder. So it's 10. So it would be 8 plus 2. So we would have, so we have 5, 10, 16. So we'd have 16 variables, 16 bits here. So 3, 4, 5, 6, 7, 8, duplicate, and print. So we need to have this one and this one. And that should be 10, because 8 and 2 is 10. And that's the instruction there. So finally, J-type, just to kind of demonstrate them all. We could have jump, and then a destination of, let's say it's, let's write it in decimal, because it's a lot of work to write in hexadecimal. Let's say 1, 2. That's too much work. Let's do something very simple. Jump to address 8. I don't want to do any complex conversions here. So jump is instruction 2, 0x02. So it would be just like that. Oh, 1, 0. And then the remaining values. So we have 6, meaning we need 26. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that should be 26. Not going to count it. And we're going to say jump to 8. So, that. So that's a jump to destination 8 or address 8 value. So that's pretty simple. And so this would put R2 into R1. This would put R1 plus, or this puts R1 plus R2 into R5. This puts R1 plus 10 into R5. And this says increment the program counter by 8. So, well, actually it says extend value, which it, so I guess I should put that in there. It's kind of, I haven't seen that before, so it might be a DLX thing. So extend immediate values are padded by leftmost bit. So, and then I guess otherwise pad left with 0. So if we have 10, it would be, this is how it would look. This is actually extend, so this should be all ones. So we have 4, that means we need 22, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There. So that's how it would actually look, to kind of duplicate what they have. So, fun stuff. So we'll see what that brings up once we get to that point, but for now, that's good enough. So I guess we'll extend that. That's going to complain. So let's put that at the bottom there. Just going to keep it separate. So that's what our instructions look like. Can't remember why we were going through that, but we were. We need opcode and parameters and stuff. So our largest argument is going to be a, well, I guess they'll all be the same length because they're all 26. So we don't really have 26 bits per se, but what we do have is we can create using bit fields. So we can say uint instruction, and then we can have a type def struct instruction, and in here we can have bit fields. So we can have opcode is 8 or is 6. Let me just look up bit codes again really quick. Bit fields. Bit fields. I haven't used them in a while, so I forget the syntax. So yeah, we have. Oh, it needs a value. So unsigned. So uint opcode 6. So this says 6 bits of our 6 bits are going to be the opcode. Actually, I guess it's not always opcode. So let's have a. Let's not do that. Let's do type def struct, and then we'll say R type instruction. And then we'll call this one an I type instruction, and this one can be a J type instruction. So in here we'll have uint, and we'll say the first 6 are zeros, 6, and then uint. Let's write this aside here. So I guess really quickly to touch on what this is actually doing, people unfamiliar with it, because it's not a common convention. This says take a uint and use the first 6 bits for 6, or the first 6 bits for whatever zeros is going to be. And then what it does, it takes the remainder of the uint and essentially discards it. It says we don't care about the rest of the uint. And I guess it depends whether it uses front or back. It might be used back. it doesn't say here which one it's going to use. But what we can do is actually go and say comma, and then uint, or not uint. So let's actually put this on new line so we can tab over nicely. So with zeros, we're going to have rs1. Just tab all this over to make it nice and clean. And it's going to be 5. And then rs2 is going to be 5. And then rd is going to be 5. And then unused is going to be 5. And then opcode is going to be 6. So I guess it formatted for me anyways. But what this is going to be is it's going to say, okay, take one uint and fill these values in there. And the reason that this is really nice is because we can use one uint for instruction, and we can basically say R type instruction equals instruction, or cast to instruction. So and then what this is going to say is, I guess it needs a R, and because we're in a whatever, yeah, it's not going to work. So yeah, this give me errors about C++ and stuff. Anyways, regardless, what this is going to do is it's going to say, okay, take this instruction, which is going to look like this R-type value here, and it's going to say, okay, so the first 6 zeros are going to go into zeros. These 5 are going to go into rs1. These 5 are going to go into rs2. These 5 are going to go into rd. These 5 are going to go into unused, and these 6 are going to go into opcode. Or it's going to do it in the exact reverse order, in which case we'll just need to flip these values around. But that's something we can look at in a second when we actually want to test it out. So, and then in here, we're going to need a uint, and we're going to have opcode as 6. We're going to have rs1 as 5. We're going to have rd as 5, and then we're going to have immediate as the remaining 16. So there we go, perfect. And then JType is going to have the first 6 as the opcode and the remaining 26 as the value. And then what we can do is we can have a type def or a union. So type def, instead of a struct, we'll use a union, and we'll say instruction, which will be a R type instruction, R instruction, or it will be a I type instruction, or it will be a J type instruction. And the nice thing about using a union is it's always going to be one of these, never all of them, never 2 of them, just one. So we can always use just the one, and it will always be a size of 1 uint, regardless. So that's the nice thing about using the union on top of the structs. So we can have a instruction, formatted instruction, and then we'll need to add function once we get our jump table set up and all that. But for now, we have a current stage, we have an instruction, and we have a formatted instruction. And right now, this is all publicly accessible. So whether we need to change that or not, we'll figure out later. But for now, it's publicly accessible, so we'll be okay with that, I guess. We'll scope it at a different point. So that's done. Um, so next would be to let's create a state and set it as our default state. And then that's kind of where we'll stop it today because this video is getting kind of long already. So let's go to our state machine, and in our initialized state machine, we'll set up a, so let's include, what's in state machine.h? State handlers, okay. So we don't need current state anymore. So let's create a, we'll remove that as well. Actually, oh no, we removed it from there. Actually, yes, because current, let's just undo that. Because we will need to store the current state that, with the way we're executing states, maybe we don't need that. Let's just create one here, and we'll just kind of make sure everything works. Creates right now. So let's go state current state equals state malloc, and because we have std lib included in DLX sim, we can call it here, and then size of state. Okay, so now we have a current state variable. So let's take a look at what's inside of it. So state handler, we have current stage, we have instruction, and format instruction. So let's go current state, current stage equals instruction fetch, and then we'll set current state instruction to be equal to 0, and current state format instruction to be 0 as well. I guess it has to be null because it's an actual object, or it's a cannot be assigned to instruction. So let's say instruction we'll see that for now then, I guess. Because yeah, we can't set a union to null because it's a union, not a struct. It's not a real pointer in the same way a struct is. Or not real, yeah. It's not a, is it an object? No, it's not. It's not a pointer, so we can't assign a void pointer to it. So we could set it to, I don't even know what we'd want to set it to. We'll just leave it for now. But now, I guess those are all fine. So now, yeah, so that's good. That's perfect. So now we have kind of a basis. Let's just see, does this have a zeroed out instruction, if that equals anything? Doesn't look like it. So I guess we can use the zeroed out as our no operation. So if we get all zeros, it's no operation, which is good to initialize it too, so it doesn't do anything. So I guess now that we have our states, kind of the basis of that handled out, which took us a little while to set up, a little longer than I thought it would. But now that we have our states, kind of a base for them, we can now, next video, start working on handling transitioning and creating multiple, all 5 states that we'll need to have access to. And then definitely next time we'll have to transition our state machine between the different states, or which the current state is. So yeah, it will need a state, current state. It will need that, which will be the state currently in. We'll need a current state. I'll give more thought to that, and we'll discuss. We'll take a look at that next time. How we're going to tackle that situation. But So yeah, this time we really just organized a little bit and then did all of this state handling here and setting up the instruction format. So next time we'll tackle a little bit more, but between then and now, I'll upload this code to GitHub. Might make a few changes between this and the next video. Again, I'll go over those if I do. Other than that, if you feel like you want to keep developing ahead, or if you want to review previous videos, you can tackle that however you want. But until next time, happy programming.